Okay, let us talk today about quite industrial topic, how much and reasonable we can scale up models in autonomy. Yeah, I'm here representing the ML research site at Neuro, like delivery, self-driving delivery company. Sorry. Okay, and let me thank our lead engineers, without whom we wouldn't have this talk. Brian, who is responsible for the behavior part of today's talk, and Joanne, who is responsible for the perception part of the talk. Okay, let's start with motivation. Like the first part which I'm going to talk today about is a behavior, because I'm from behavior mostly. And when we're talking about behavior, we would like to understand whether we can reasonably well scale the models in order to, for example, overcome overfitting. Because usually behavior models are smaller than perception ones. They are not so big. So is there any chance to scale it reasonably well? Also, we'll talk a little bit about perception models, whether it's practical to scale them up because they're already too big, to be honest. And like the approach is quite simple. Let's do the ablation of model capacity versus model size, data training size, but we would like to be practical. And if we are practical, we would need to fix our computational budget. Okay, so our goal is to understand how better can we scale up and go with scaling up the data, training data, for example, and model size. Yeah, very simple. Let's do ablations. The second one, goal, which is very tied to our industrial experience, we need to be practical. So how practical is the scaling? And yeah, let's do this limitation or condition on our scaling loss. So we would like to stick to some computational budget. Okay. We know, like, starting from 1 or 2 years ago, we've been seeing a lot of papers concerning computer vision large language model scaling loss or power loss. They're cool. They have billions or even trillion parameters. They can be trained on the lab scale data. But can self-driving industry benefit from it? Yeah, let's try to provide some statistical. I would like to emphasize statistical. It's not like direct, I don't know, recipe here. So do we need larger models, or do we need more training data? And can we do it with some fixed budget? Yeah, some nomenclature here, like, but quite simple. N is the number of weights, D is the number of samples training data set, S the number of iterations or epochs in training, and C the computational budget. Usually measured in flops, floating point operation. Usually this number of flops is proportional to the multiplication of training steps and the size of the model. Yeah, and we have loss metrics. It can be training or eval. For sure, we are much more interested in the eval, but we are starting with the training for sure. Okay. And basically speaking, we have two types of scaling loss. One is we would like to understand what are the limits of model performance, how it can be improved with more data and more weights. And the second one, when we have this restriction on the computational budget, how far can we go under this limitation? And for the second type of the law, so we would like to have this arg minimum of L and DS, where L is our training or evaluation loss. We can use very simple patterns because I think like everybody understands that we have this power loss. So we can have like N is some constant multiplied by some C to the power of alpha n, and S is some constant multiplying by C to the power A alpha S. Okay, doesn't matter. So let's start with the model itself. Very rough idea. What model we will be using for our experiments is so-called behavior encoder. Let's study this loss. For some standard transformer-based encoder model. So to the left, we can see some environment, our, for example, here, new robot, but there's just some ego. We can have some agents around. So we're using some, I don't know, classical transformer-based encoder. And we have a lot of different task-specific decoders for prediction, for planning, for simulation, for scene generation, for scene understanding, doesn't matter. Yeah, what experiment details settings that we used? For model capacities, we start with 1x, 4x, 8x, 16x, up to the 32x. For some data sizes, we just were limited more and just used 1, 2, 5, and 7. What I would like to emphasize here is that we used the same total batch size. Yeah, when we have bigger model, we just used less batch per GPU, but we have more GPUs. For GPUs, we used 40 gigabytes A100. Training times varies from 1 to 14 days. The same schedulers we used, yeah, and for metrics, we used train and evaluation losses for behavior encoder, so such sort of prediction and planning metrics as well. Yeah, and our base model here is like 4x. Okay. For scaling loss, we are using usually the best checkpoints. Loss function is modeled again as a sum of powers of n and d, where the E is a reducible error, even for infinite model. A is a weight for imperfect model used by insufficient capacity, and B is a weight of perfect model caused by insufficient data, and some power law parameters. Okay, let's start do some experimentation size. So we collected a lot of triplets L and D, this top right, and then we just can feed the model performance scaling function. And conclusion is the following, quite simple. So the better performance we can see with the larger N and D. So more weights, more data, everything is cool. And this is the red square in the bottom right. And also what is important, so suppose we would like to improve our training loss by 1% or by 5%. So we could have this dissecting plane, and we can see this profile, which is like marked by arrow. The same can be done for number of training steps, where we just use LNS triplets, and there is the same conclusions, very simple. But we can even compare the train and eval losses, because what we really care of, we care about eval, not about training. And we can, if we, for example, can do this subtraction of eval versus train, and we can see that with a larger model and longer training, we can really bring these losses closer. That is really cool. Yes, these settings, ideal settings are nice, but what about practical limitations? And let's look into this. Usually it is done by so-called envelopes. So let's stick to the largest data sets that we have, like 7x, and start with the training loss at varying estimated flops C, computational budgets. So you can see on the this diagram a lot of points of different color. Different color corresponds to different model capacity. And x-axis is the computational budget, and y-axis is train loss. The lower, the better. Yeah, and what is optimal capacity here is the lower envelope of these curves. Yeah, and we can see that for different C's, optimal capacity can belong to different models. That's very important. So we cannot just train the smallest one, or we cannot just train the biggest one and just hope that it would solve, it would be sufficient for every capacity budget. No. And yeah, about the notion about colors. So, okay, let's fit and to understand the predictive power of it. The approach is quite simple, is we using the lower envelope to fit the power law between N and C, number of weights and capacity budget. We can do linear regression and log scale. We can do it in linear scale as well. And to the right, you can see this dependency of N versus C. So you can see like this piecewise linear function. So the bigger C, the higher N for the optimal model. Yes, and this is like smiling faces is our baseline model here. The star means that, for example, right now we only have experiments up to the computational budgets of 10 to the power 16. But what if we would like to stick to the computational budget in the future, for example, to the power 10 to the power 18? And we can somehow hypothesize and predict how much capacity do we need. And you can see here like almost 100, like 72x. The same can be done when we just need to understand how long do we need to train. This is amount. This is the number S. This is also very important. So how long we can wait for the first model to be trained in order to see the result. And again, you can see the same, the quite similar, also piecewise, but not horizontal lines, because S can be the amount of training step can correspond to different C. Yeah. And yeah, that's cool. But we would like to understand, can similar scaling laws can be applied to the different settings, for example, evaluation laws? Yeah, so we can do quite the same. Again, lower envelope, different models with different amount of weights. And here observations are the following. So the smaller models diverge after training for a while larger models are not even fully converged. So we have somewhere sweet point between them. There are some hypotheses, probably may relate to some like very interesting effects like double descent or broken neuron scaling loss. What is also important that small models like 1x and 4x converge fast, but they're unstable. And larger models converge too slow, as you can see here. Yeah, we can do the same amount of experiments with the same nature. We can find the model capacity and star for a given cost budget. And we can see that for eval, we can have here a little bit different amount of capacity, for example, 112x in comparison to 72x that were estimated for a training loss. So it seems like training is more optimistic. It's overemphasizes the scaling law, but in reality, we need to have bigger model. The same for S, and again for evaluation, yeah. But here, like training loss is providing us a more bigger amount of steps to have our model fully trained, but for a while we need less. That's also interesting. Yeah, we played a lot with different train and eval losses, but yeah, much more important for autonomous driving is to have some downstream metrics like mean ADE, for example, or some planning losses metrics. Yeah, and let's do some optimal model scaling with prediction model, with prediction metrics. Yeah, and here we used mean ADE, minimum average displacement error at 10 seconds. And we have three major object track types: vehicle, pedestrian, and cyclist. Yeah, and we can do it on the very simple and the same approach that we did before. You can see this diagram on the left, and on the bottom you can see the three different estimations for the 10 to the 18, I guess. If you can plot these three curves, just I use this Wolfram alpha for it. So we can see that they are quite close. It's very good because they're consistent. So it means that we can use the same model. The same model for it. We don't need like a different model for vehicle, pedestrian, and cyclist because the at least the capacity is quite the same. Okay. So we played a lot with some simple method, but we would like to concentrate more on the specific budgets. Probably we have some options from our, like, I don't know, data center provider. So you can use either this amount of flops or this amount of flops or this amount of flops, or probably you can pay this amount of money or this amount of money. So we've done our method one with varying flops, but let's fix some flops to find optimal model. So algorithm here, we define multiple C levels. Yeah, they can be found here. Yeah, for each C level, we can plot the profile curves, and we can find the model capacity that has the lowest training loss. The lower, the better. And here you can see that each curve corresponds to some specific capacity budget or money budget here. Yeah, and the lowest point corresponds to the better model that we could get out of this capacity budget. Yeah, and again, we can do very same computations, very same curve fitting in linear or logarithmic scale. So it doesn't matter. What is important here? We can do the same for eval losses, and some finding that the biggest our model 32x model performed better, even better on lower flops. Is quite interesting. It seems like it learned fast in the very beginning of the training. Usually it's like takes longer to train larger model, that's understandable. And 32x model probably is not trained to its best. And again, you need much more, like, I don't know, computational budget for it. Yeah, and we can again compare it with what we provided for the training loss. You can see for the training, we were much more optimistic. And here we were pessimistic probably. What is interesting here, we can compare these two different methods. The first method that we talked today about was much more fine-grained because we can play with like almost every C point, but usually we have a very specific, I don't know, levels of C, computational budget. Yeah, this is method 2, and it seems like method 2 has better correspondence between train and eval predictions. Because, for example, here, like the second and the third row, you can see the difference is probably 1.5x, but for the first and the last row, which is for the method 1, we have almost 2x. Yeah, and we can see, for example, for our target capacity 10 to the 18. So best model capacity is something like 100x, and the training step is something like 10 million. Just as comparison, the baseline configuration is 4x, and it's like orders of magnitude less steps that we need to train it for the C1.4 e to the power of 15. Okay. Let's jump to the most important part here. This is behavioral tasks, because behavior, like our behavior encoder is shared between different tasks. And yeah, let's use two major tasks, prediction and planning. For the prediction, we used about 175 kilometers. It's about 15 hours of driving. Major metrics use MinIDE. For planning task, we used a little bit less data, it's 125 or 10 hours of total driving, and our major metrics is so-called passes. They're quite rigorously used counts. For example, when we are finishing as a specified zone, or when we are like coincide with some predefined, I don't know, events or metrics, or also some kinematics or dynamics limitations. They are mostly counts. Yeah, and we used usually here final checkpoint. We didn't do this like the best one because of some limitations. We initialize the prediction and planning models from it, and then freeze the behavior encode and fine-tune model decoders. And these are the result of this fine-tuning. So we can see that here are different curves for different model capacities. For training data set size, yes, we have usually the more data we have, the better decoders are. But again, some interesting observations. So smaller models scale when data set is small. So they do not have enough capacity to play well on the biggest scale. And then start to overfit. The sweet point here is 16x model, which scales almost linearly. This is the lowest curve here. And the biggest model significantly overfits when data set is small and didn't fully converge. So probably we need to wait a lot more than the amount of budget that we had for this experiment. Yeah, and the very interesting and probably the most practical use case here, suppose we just did all the experiments with train and even eval and even with some downstream metrics. But what if at some point our model just changes and changes not in terms of, I don't know, number of layers or like the width of some layers, because almost all the experiments before that I described were using like different widths of the model. Some layers. What if just changed somehow the architecture itself? Like, for example, we can use different points where we do the cross attention, or we are adding a little bit different features from the training data set. Would this scaling law still be applied? Yeah. And let's try to do this experiment. Let's check our predictive power of all this, what we have seen before. And for the scaled model, yes, initially we have this 1.4 multiplied by 10 to the power of 15. Let's allow for us the computational budget up to 10x. So we did like 3 different target flops levels, 10 to the power 16, 1.4, 10 to the power 16, and even 2 multiplied by 10 to the power 16. Yeah, and we have a train and eval losses, and here are the optimal model sizes. And we can see that the nearest, I don't know, candidate that we had before, it was 16. So let's hypothesize that 16 would be the better model here. Okay, and let's make this 16 model for the new, slightly new, but still new architecture. And what we can see, that scaling law really can be transferred to different, at least slight different architecture. So we can see here from when we're jumping from 4x to 16x, here the because mean ID is the lower the better, so we can see minuses, and we have up to 7% better. And also, like this is for prediction, for the planning, we also have improvement in 3.5%. That's nice. That's really what we would like to see for the whole this research. And also, like some of the observations is that advanced model, the new one, the newest architecture, benefits more from the scaling. It's also cool. Yeah, everything that I talked before, okay, was mostly about behavior, but also like, to be honest, we started with the perception probably 1 year ago. And one of the most important tasks for perception is to do object detection. And we did some experiments with conv-next as a backbone in an object detection model. Yeah, this is conv-next block here. You can see here which specific model capacity models did we use, and we can see that when model capacity grows, the also increase in terms of in inference and memory just quite linearly, their lines. Okay, we can do quite the same as we did for behavior. We can collect the LND, so loss, amount of training samples, and amount number of weights. Can collect these triplets, can find some specific point, and then can do this fitting exercise. Yeah, and we are here using MAP metric, mean average precision, as a performance one. What we can see that better performance with a larger N and D, and this is this red circle. And again, we can fix L, for example, and we can find out the needed ND profile. And this is exactly the same conclusions as for behavior. Nice. We can even play again with C versus metric. And we can see here 2 vertical lines. This is our computational budgets limitations that we did for behavior. For perception, as you can see here, we need much more. And we can see that for 1x model, superior performance in a low flops regime. And we really need much more, I don't know, money to do this perception scaling law experiments to this limit. And we didn't succeed here. So conclusions are similar, but not exactly the same, because we don't know, for example, what could be here, like in the top right corner. Yeah, we also tried a little bit experimentation with the data set size for perception as well. We can see that model scaling again works, but requires large data scale. For example, when we have 7.5 amount of data from our original data set, improvement is smaller and plateaued at some point. This is the upper curve. It just starts to plateau, to make this plateau. At 50%, this is, I guess, the lowest part. We can see almost linear increase in performance, but we need a lot of, I don't know, GPUs and money to do these experiments to this limit. And it's really costly. So yeah, latency, model size, and cost increase extremely fast. So to conclude the perception experiments, I would say that we have probably not exactly the same, but similar results as for behavior, but we need for perception a lot more computational budget. Okay, for the conclusion. What could be the possible next steps? First is better understand width versus depth differences and learning rate impact, because almost all the experiments that I showed before were targeted towards increasing the width of the layers. Very simple. Yeah, very interesting how can we really go to the point when we can see the double descent? That's unclear. And would be interestingly, yes, to go to this range of 10 to the power of 12 or even upper, and to see whether we can still see this scaling loss prediction power. Limitations. The major limitation from my point of view here is the following. So what we are doing with this like upper envelope or lower envelope is a sort of extreme statistics. And this is, we are working with extreme models. So we can really lose model which can have like performance minus epsilon, but can be order less complex or would require order less data. That's the limitation, the major limitation here. Yeah, that's quite obvious thing the manager realize. Yes, and the second very important thing that all these things that we've tried can really add us some additive improvement, but the cost is multiplicative or even exponential. Do we really have the opportunity to do it? That's the question. And yeah, what like the practical I don't know, bounds and the practical problems that we face during this research, that we need really reliable infrastructure. Because when you're doing all these experiments, you can just, I don't know, if you have some probably errors and bug in the code, or for example, if you have in this infrastructure some not reliable, I don't know, connection between GPUs and between data center, that's not going to work. You're just losing a lot of money for nothing. And you need fast experimentation pipeline as well. So you need to establish how to collect all the results, how to do it in an automatical way, and how to, for example, rerun the experiment in order not to wait in the queue for experiments too long. Yeah, conclusions, scaling laws are applicable. They are working, at least when we are using the reasonable amount of budget, and they have predictive power, autonomous driving as well. We can use different extrapolation methods. They have their pros and cons, but they are mostly coincide in the order, and that's nice. Yes, and even without significant change of the model, but at least we can allow for some model change, we can do better, just longer training, just more capacity, and just more data. That's the main outcome. But here, like, I don't know, some, like my subjective point of view of all these things. We can understand this scaling loss approach is sort of trivial way, a very trivial way how to add a handful of percents, which is quite we can draw some parallel in terms of when we do some Kaggle challenges. So we can do some ensembles, and this you're almost all the models that win the Kaggle challenges, there's ensembles of like 100 of models, 1000 of models. So we can do it. And what is nice, we can even forecast how big the models we need, how much data do we need. But at the same time, it's not a game changer. So we can allow for slight marginal improvements, but only in terms of very extreme high costs or like orders more data. For example, yeah, having 1,000 times bigger models, GPUs, or data. And here, yes, I would like to, I don't know, to make the bridges between different companies who currently work in the autonomy industry. Would not give you the clear preference of other companies. It's just not going to work. You can add plus 1%, but it wouldn't like change your, I don't know, competence power on the market. And yeah, as a result, so we still need better ideas. Probably LLMs right now, they could be a sort of game changer, but still even, I guess, for all LLMs, all the scaling laws would be the same. And again, we can go up by one step. And again, what to do? Yeah, and visit our poster today. Jonathan is presenting the poster for multi-constraint safe RL with objective suppression. Because at Neuro, we are really, really concerned about the safety, and this is our main goal. Okay, thank you.
All right, if there's any questions from the audience, please raise your hand. Yeah.
Yeah, thanks for your talk. You have some pretty cool data. So from what I can tell, like all your conclusions seem very much in line with like the natural language processing field. Like, are there any obvious differences that you picked out as well? Like, is it, this data type, is it just the same? Is it because of the transformers that everything scales the same? Do you have any feeling for that?
Okay, thanks for your question. To be honest, in the very beginning, we were very skeptical about application of scaling laws in the autonomous driving. Also, like, yeah, transformers are the same. Like, doesn't matter whether they're in computer vision or behavior or in like perception. The metrics are a little bit different, especially for behavior. So that was our initial motivation to do it. For example, whether the scaling laws can be applicable for a very different style of metrics, and whether we can, for example, with some model change, we can still have this predictive power. And it seems that yes, whether the source of this, I don't know, coincidence with the computer vision world is using of transformers, I'm not sure. Probably.
Thank you.
Thanks for the great talk. I really like those scaling laws, but do you also have any like qualitative examples? Because for LLMs, we also see some like emerging capabilities by like scaling up the model. I'm just curious, for instance, comparing the 32x model and the baseline model, do you see any like emerging capabilities in terms of some qualitative examples?
I see. Thanks. I think first of all, we didn't do like very rigorously the the comparison qualitatively, like 1x versus 32x. We did a sort of look into like top errors or top like winnings. This looks reasonable, but not like emergent. I guess emergent capabilities probably would be raised when we have like double descent, but we are not close to this point. That's why I just put it as one of the the next steps. So currently, I wouldn't say that we have this emergent, to be honest.
If there's any other questions, go for it.
Following up on the previous question, how far do you think you're away from that double descent?
5 orders, probably. Yeah, but at least like I think like currently we have this for this legal issues. We don't need to train up to the 10 to the power 25, right? But here we are not even close to the 10 to the power 20. So I guess like double descent probably can be somewhere lower than to 25, probably 1023. But yeah, we are like, again, like 5, 7 orders. At least for this experience, we have 5, 7 orders less, unfortunately.
Yeah, I guess maybe related, like in LLMs, right? They became very useful once they started adding like RLHF on top of this pre-training recipe. Yeah, I'm wondering if you see that a similar benefit for that, like some sort of fine-tuning step on top of this pre-training.
Yep, for sure. And this is what we are playing right now. Yeah, definitely. They can really be understood as a sort of probably not game changer, but that it can be a game changer in terms of how do we collect data and how do we label it. Because yeah, to have this preferences is much easier. It's much more aligned with what we would like to see, like human triage would do. So yeah, from this point of view, it's really useful, and we already can see it like in our research. Yeah.
Any other questions in the audience?
One of the advantages of scaling LLMs is they're pretty data efficient, where you're doing prediction and loss on every single token in your text. Whereas with behavior prediction, we're training over fairly large scenes and longer horizons. Do you think that, we have work to do on maybe trying to improve our data efficiency to improve these scaling laws?
Thanks. Very nice question. Yeah, I think like especially in the industry, when we when we don't, I think like it's very tightly connected to the not only to the data pipelines and also like to the metrics itself. I guess when we're inside the industry, usually we don't have, I don't know, the clear path towards like challenges of very well established and formal metrics, etc. And the data pipelines as well. So I guess yes, and probably even significantly we are dependent on the, I would say, very well established data pipelines and metrics around it. I would say yes.
Any other questions? One question I had is, so you've got these scaling laws, and talking about extrapolating, and how many orders might be needed to achieve certain emergent properties or certain performance guarantees. I wonder, is there anything, like, given it's an extrapolate, like if we extrapolate out, is there anything else that could interfere with that extrapolation that you're aware of? For example, the data sets that you may be using or Neuro may be using, like, is it limited, and could that be a natural cap? Or maybe discrete models are having a real comeback now, like maybe the discretization chosen kind of caps some of these performances. Is there anything that you think may disrupt the trend when you extrapolate?
Yep, very nice question. Definitely we are biased towards the, how to say, the nature of the data. For example, what would be if we put more synthetic data into either training or eval? What could be if we would have much more collisions or near collisions? Yeah, because mostly what we are training on is like usual common data, probably sometimes quite interactive, but still very boring. So yes, and about like also like about the model discretization as well. So it's still like all this extrapolation in terms of, suppose we would add the same distribution of data, or we would work on the same, I don't know, similar architectures and the similar metrics. If we are changing a lot, either metrics or data distribution or architecture, I guess it would be broken. Yeah.
Yeah. Okay, cool. Yeah. I think the only other consideration I could think of is you mentioned 10 to the 25, I think, for certain emergent properties. I think from memory, the Biden's executive order was 10 to the 26 flops. So that might be another limitation where you then have to email the White House for permission or something. To...
26 years.
Okay, yeah.
I just forget.
Yeah, so I liked your last slide, the segue into your poster, and that segue is really nice for us as well into our final poster session.